Yeah, so I'm ready when you are. When you give me the green light, I'll just go ahead.
So I start recording, so it's fine to go now.
Yeah, so thank you everybody for joining us today. And today we have Mihaela Rosca from DeepMind giving a talk on the importance of discretization drift in deep learning. So very happy to have you, Mihaela, today. And please, the floor is yours.
Yeah, thank you so much for having me. As I was saying earlier, I actually did my undergrad and my master's at Imperial, so it's kind of really nice to be back. It's been a while. And yeah, I'm working at DeepMind. I'm a research engineer there. I'm also doing my PhD at UCL at the same time. And today I want to talk about exactly what was just said, the importance of discretization drift in deep learning. So a bit of an overview of what this talk is about is, firstly, what is this quantity discretization drift that basically the entire talk is going to be about, its importance in supervised learning, and its importance in GANs specifically, and then more generally in games, and then just a little bit of a teaser at the end on stochasticity and discretization drift, which is something that I won't have time to talk about in detail today. Just as a very clear disclaimer, a lot of this work is not mine. I thought it would be more useful to give an overview of this small subfield rather than just focus on my own slides. My work will be present here, but it's not the only work. So I'm just going to try to make it clear which paper to look at when, and just to be clear that a lot of this work is done by some of my co-authors or others completely. So with this in mind, the relevant papers for this talk, there are 4 papers. We're going to primarily focus on 3. The first one is called Implicit Gradient Regularization by David Barrett and Benoit Durand, which tackles discretization drift in supervised learning. Then there is the work of training generative adversarial networks by solving ODEs by Chong-Li Kim, Yan Hu, and their collaborators on reducing this drift in GANs. Then there's the work of discretization drift into player games led by myself, and of course my collaborators, and then also on stochasticity and discretization drift. So beyond this work, there's a lot of interesting related work out there, which of course I won't have time to cover, but each of these papers has, of course, a related work section. So if you're interested, there's a lot more to look at there. So let's start with what discretization drift is and why we would want to understand it. So the goal of a lot of what I'm going to talk about today is to understand discrete optimization dynamics, such as gradient descent, through the lens of continuous dynamics, which closely match these discrete dynamics. So we're going to leverage a lot of what we know about ODEs, and I'm going to use interchangeably the word ODE or continuous flow or flow with the discrete dynamics of gradient descent. And just before we delve into the optimization side, I just want to highlight what I like to call the return of continuous dynamics in machine learning. So obviously today I'm going to talk about optimization, but I think we have seen this a resurgence beyond optimization. So if you follow the neural ODE line of work, you've seen how continuous systems can be embedded into neural architectures, or in generative modeling. Quite promising line of work is to have continuous time normalizing flows, approaches such as Fjord. So this seems to be a little bit of a trend. And one natural question that we might ask is, why are we interested in continuous dynamics? Well, continuous dynamics tend to be easier to understand and analyze compared to their discrete counterparts. And there's a whole field out there looking at trying to understand ODEs using methods such as stability analysis and more. But also, if we specifically focus at optimization, they do provide a little bit more guarantees, right? So we know that if we want to get to a local minima, if you go in continuous time into the direction of the negative gradient, you're going to get there. But in discrete time, you might just jump over that local minima. And indeed, this is what we're going to talk a lot about today, about continuous dynamics for function minimization, their discrete counterparts, and how to use continuous dynamics to better understand discrete methods such as gradient descent. So for now, assume we have a function e that we're trying to minimize with respect to parameters phi. So these parameters are going to be very high dimensional vectors, such as the parameters of a neural network. So what we know is that, well, we want to minimize this function, then we want to go into the direction of the steepest descent, right? And we want to do that in continuous time, but of course our computers are discrete. So what we will do is we will discretize this continuous dynamics using numerical integration methods, for example, the Euler method, and obtain gradient descent, which is what we use in practice quite successfully, I think. Now, in terms of notation, sometimes I'm going to write things a little bit more generally, just because the math that I'm going to talk about is often more general, but underlying, we often have in mind gradient descent. And when I say more general, as before, I talked about this ODE, about the change in parameters in continuous time going to according to the negative gradient. Sometimes I'm just going to write a function f, and a lot of the math holds for a general function f. Now, again, if we use numerical integration, we don't call that gradient descent because there's no gradient necessarily, but that's the Euler method. And we get gradient descent if f is the negative gradient. And now this slide is quite important. This is the definition of the drift. We now have all of the concepts that we need to define the drift. So what we started with is we're saying that, oh, we actually want to follow a continuous system. We want to follow the negative gradient in continuous time. But we can't do that. So we're just going to use a discrete method, such as the Euler method. So we're just going to do something that makes basically a jump from iteration t to iteration t plus 1. You do this discrete jump. But you can also ask, well, what would have happened in that time, which is given by the learning rate? So the learning rate is the counterpart of time in continuous time, had we followed the underlying ODE. And we know that for the case of Euler methods, so for the case of gradient descent, this error is of second order in learning rate. So we have an error because we're not directly following the ODE, and that error is of second order in learning rate, and we're going to see that this error can be quite important. And this is what this talk is about. How can we understand the effect of this error from what we want to do to what we are actually doing on deep learning systems? And we're going to see that in supervised learning. We're going to see that in GANs. We're going to see that in other games. So this is what we're talking about today. And a lot of the approaches that we're going to look at look as follows. So this approach was introduced by David Barrett and Benoit Deron in their implicit gradient regularization work presented at ICLR 2021. And what they say is, well, continuous systems are quite nice. How about we introduce a modified ODE? So this is the ODE that will often have a tilde in my notation, that doesn't have a second order in learning rate error, but rather a third order in learning rate error. So we're reducing not only the error, but the order of the error. And this approach is inspired by, and it uses a numerical method technique called backward error analysis. And I'm going to talk about that in a second. Now, why would we want a modified ODE? So if we go back to the introduction of the talk, I said, well, continuous systems are quite nice because we can understand them, we can do stability analysis using them, and we would like to then now leverage all that information on continuous system to better understand discrete dynamics, which is what we use in practice. And this is the approach that they take, and this is the approach that we will take later on in our work as well. And just to visualize this approach one more time, we start with the continuous dynamics. So we have an ODE that tells us how the parameters change in continuous time. But in practice, we will use numerical integration that will give us a discrete system, discrete update. So, and this, in the case of Euler updates, this is the case for gradient descent, introduces an error of second order in learning rate. And what we will do is we will invert this process by starting with discrete dynamics. So we start with Euler updates, we do backward error analysis, and then we find some continuous dynamics which better match the discrete dynamics. But backward error analysis tells us something else. It also tells us the form of this modified ODE that we want to find. So what's nice is that it has this very nice additive form. We have the original ODE. So remember, the original ODE looked like this. So this is exactly what we have here, plus another term which accounts for this discrepancy up to second order in learning rate. So it has to be proportional to the learning rate, to reduce the signs of the order, but we have additional this function f1 here that accounts for the drift dynamics. And a lot of our goal, either in supervised learning or in games, is going to be to find f1. In games, we're going to see that we're going to have two functions for each player, but the idea is the same. Backward error analysis tells us that we need to find some other ODEs. It prescribes us the form of these ODEs, but our goal is to find f1 such that our error is smaller after one step. And now there's something else that we can do with this modified ODEs, apart from using a lot of the tools from continuous systems. Often, we can go from modified ODEs to modified loss functions. So implicitly, we can better characterize what gradient descent is actually minimizing, which can be quite useful, as we will see in a few examples. But let me give you again a bit of the recipe of how we get from modified ODEs to modified loss functions. Remember how we started with the loss function, and then we obtained the original ODE as the changing continuous time of the negative gradient. So if we can write the right-hand side of this ODE as a negative gradient, that would mean that implicitly gradient descent more closely follows that loss function. And this is exactly what we do. So we can choose our f. Let's say in supervised learning, we know our f is going to be the negative gradient of the parameters of the loss with respect to the parameters. We'll find f1. I'm going to show you how we can do that in a bit. But assume that we can write f1 also as a negative gradient. Then we can write the right-hand side of this ODE as a negative gradient, which means that we have some dynamics that better describe what gradient descent does. So this is gradient descent. These are our new dynamics. And these dynamics here, the dynamics here in green, minimize a function. This is not our original function. It's a different loss function. But because gradient descent more closely follows these green dynamics, we can say that implicitly, every time we use gradient descent, we're implicitly minimizing a modified loss function, which of course is going to be related to this original loss function. And I think this is a very, very important tool to understand gradient descent, is that, well, maybe you're implicitly minimizing some terms, which can be have a positive regularization effect, as we will see in supervised learning, or it can be problematic, as we will see sometimes in games. So this is basically the main message of the talk, that we will sometimes want to use continuous systems to understand gradient descent. And sometimes we can go from continuous systems to modified loss functions, which can better describe what gradient descent actually does. So now we can see how they did this in the context of supervised learning. And this is, again, work by David Barrett and Benoit Deron at ICLR 2021. So just to introduce again the context, we have our continuous dynamics that we start with every time we do gradient descent. We do numerical integration and we end up with gradient descent. And we're looking for this modified ODE of this form that is given to us by backward error analysis. And our goal is to find f1. And the idea, this is the only kind of proof that I have in the talk, but I think it's quite illustrative and the idea is quite simple. So we are going to basically do a proof by construction. If we start here, we can ask, after time h, where will this ODE be? And to do that, we can perform a Taylor series. So this is our ODE. It has this form. We know how to do Taylor series. We do a Taylor expansion. And now if we replace the value of the modified ODE to that one given by backward error analysis, we end up with this form for the modified ODE. The exact terms for now don't matter. It's just that the important part is that we're questioning, where are you after time step h in this continuous time system up to third order in learning rate, because that's what we're interested in finding. And we are just doing the Taylor expansion for up to third order. Now, what's important here is that our f1 is in here. We don't know f1 yet. For any ODE that looks like this, we can do this expansion. Now, our goal now is to find f1. But we know that we want to find f1 such that this error is of third order in learning rate. So that means that this expansion needs to match what we did in discrete time. But we know what we do in discrete time because we do gradient descent, or in the very general case when we write it like that, Euler integration. So what we do is we can just match terms. So this term, if we started at phi t minus 1, it's exactly this term, nothing to do. HF is HF, but gradient descent doesn't have a second order term. So if we want to find this ODE that better matches this, this gradient descent, this term needs to be 0. So this is how we find F1. Using backward error analysis, by doing this Taylor expansion in continuous time, we found the value of F1. It has this, this form. We can replace it into our continuous dynamics. And now we have found the modified ODE, which better describes the dynamics of Euler integration. And this we did by this proof by construction. Now we can specialize a little bit. So these are very general modified ODEs, which hold for various f. But here we are interested in f being the negative gradient of the loss function because we're interested in supervised learning. So now we're going to go through the recipe that I highlighted at the beginning. We chose our f. Now we want to see whether we can write the right-hand side of this ODE as a negative gradient so that we can find a modified loss. So what we're going to do is that we're going to write F1. We now know the value of F1 through the proof sketch that I just showed. And we are just going to replace the value of F with the one that we've chosen. And we see that we can write the right-hand side of our modified ODE as a negative gradient. So that means that when we are back to our visualization, every time we do a gradient descent step, this is the flow that minimizes E. And this is the flow that minimizes the modified loss function, which looks like this. So implicitly, you are more closely minimizing this other function, which says something very interesting. So now I'm just going to pause a little bit to look at this function, because what this function says is you minimize your original loss function plus this term, which says you need to follow shallow paths to the local minima. You can have, it's basically penalizing large gradient norms. And this is what they call in their paper implicit gradient regularization, that the effect that in supervised learning, when one uses gradient descent, one is also automatically regularizing the model such that the gradient norm is small. And I think this is quite a very interesting insight that they had in their paper. But beyond the theoretical insight, they go on to show how this can be useful in illuminating what happens when one uses gradient descent in practice. So one thing that they are showing is that implicit gradient regularization can explain the convergence of gradient descent to flat minima. And here, bear with me for a second, because I'm going to try to explain what they did, and I think it's very clever. They say the following: well, the strength of this regularization is proportional to the learning rate. So this is our H is always the learning rate. So we expect that the higher the learning rate, the more implicit gradient regularization you have. And the way they show that is they train multiple models with different learning rates. And they show that the higher the learning rate, once you've converged, if you perturb your parameters around that local minima where you've converged, you can see whether you have a lot of slope there. So is the gradient norm high or low there? And what they see is exactly that for if you have a high learning rate, you need a lot more parameter perturbation to get high gradients compared to a small learning rate, where immediately, if you use a small learning rate, if you switch your model a little bit, you will get a higher slope. So basically, using this approach of parameter perturbation, they're able to show that, yeah, if you use high learning rates, you will get to flatter regions of the space, because when you perturb around that area, your gradient is still going to be small. What else they show is that implicit gradient regularization aids generalization. So basically, for different networks of different sizes, if you have the higher the learning rate, the more it helps test accuracy. And of course, implicit gradient regularization is actually also proportional to the number of parameters, because the square of the gradient norm is a sum over all gradient norms in the network. So they look at that as well in this context. What else they show, and I think this is where having modified losses is extremely important, is that they looked at the implicit regularization that happens every time we use gradient descent. And then they analyzed it and said, well, is this good or is this bad? And they show this positive regularization effect. And then they ask the question, well, can we use explicit regularization? So change our loss function not implicitly through gradient descent, or not only implicitly through gradient descent, but add an explicit regularization term to further increase generalization. And the answer is yes, that if you add a regularizer of this term, that this form that penalizes the square norm, you can further increase your test accuracy using this explicit regularization rate. So that's on the supervised learning side. So to summarize a little bit of the supervised learning side so far, in supervised learning, gradient descent induces an implicit regularization effect that one can see through this lens of the modified loss function. Higher learning rates increase regularization and help generalization. And adding explicit regularization to your supervised learning objective can help beyond what gradient descent does and increase your test set accuracy. So far, hopefully I've convinced you that there is a beneficial effect of this discretization drift in gradient descent. So this error between what gradient descent does and what the continuous flow would do if we have followed that. Now we're going to switch gears a little bit, and we're going to look at GANs, and something maybe perhaps unintuitive after what I've just said, a work that shows that reducing the drift improves GANs. And this is work done by Chonghli King and Yan Wu at the NeurIPS 2020, and the model that they introduce is called ODE GAN. So just a very brief introduction on GANs. What is different here is that we will have two models. And in GANs, we have a discriminator and a generator. And the goal of the discriminator is to answer the question, is the data that I'm seeing, is it real or is it generated by the model? So it learns to distinguish between real and generated data. The goal of the generator is to generate data that is so good such that this discriminator cannot tell anymore. It's just like, okay, I think that this could be real or this could be generated. I don't know. And in the original paper, this was written as a zero-sum game. So whatever the discriminator gains, the generator loses. And the discriminator was a binary classifier. So it classified real data as, let's say, label 1 and generated data as label 0. But since then, this field is extremely prolific and extremely interesting. And there's been a lot of different losses. Not all GANs need be zero-sum. And actually, this was introduced and shown from the original paper. And thus, we're going to talk about GANs in a very general setting, where we have loss functions LF and LG. And of course, we're going to talk again about the underlying continuous dynamics. So we have the discriminator parameters. I'm going to denote them by phi. The generator parameters are going to be theta. And what is different here and important is that f, the update function for the discriminator, depends both on the discriminator parameters and on the generator parameters. And we're going to see later on how this is extremely important in the context of games. So these are the general GAN dynamics. Now, there's something really interesting that can happen in these kind of two-player games like in GANs, and I'm showing this in a plot here. So imagine you have a very simple game with one model has one parameter. So let's say we have phi here and theta here, and we have an ODE, the original ODE that described the games has this trajectory. So it converges to an equilibrium, but Euler updates, so the gradient descent version does not. So we see here that the drift is really important because we're going from a model that gets to a local minima to a model that does not, because we are using these discrete methods. So the idea that they had was, how about we don't use Euler updates? We have higher order numerical integrators that we can leverage. So going back again to discretization drift for Euler updates, remember how I showed that it's of second order in learning rate. But what they do is they use Runge Kutta 4. And Runge Kutta 4 has a 5 order in learning rate error, so much smaller error. And what they show, for example, for a similar example to the one I've shown before, is that when the Euler integrator gradient descent diverges, so you see it's going away from the equilibrium, Runge Kutta goes to the equilibrium. And this is something that one would want, because you want your model to go to a local equilibrium rather than go away from it. And they wanted to use this in practice to train GANs. So let's replace gradient descent with Runge Kutta 4 and then see what happens. They noticed 2 issues. Sometimes the generator gradients would be exploding, and there's also the noise from the mini batch. So the way they solved that using an explicit regularizer. So a bit of an underlying theme of this talk is that explicit regularizers can be, of course, extremely useful. And they often, in this talk at least, have a similar form of penalizing gradient norms. And what they do here is something very clever, which you can do in the context of games. You can say, well, I'm not going to add to the generator to minimize its own gradient norm, but rather I'm going to tell the discriminator, update yourself such that the generator has a small gradient norm. And using this, so this explicit regularization and RK4, so Runge Kutta 4, they're able to get really, really interesting and very good results on GANs trained on CFAR10. So for example, here, we're looking at inception score and FID. Inception score higher is better. On the left, FID lower is better. And they're comparing the Euler update here to RK4 and RK2, which is a smaller order integrator. And what they see is, so remember, higher is better, much better performance from RK4 and better stability. You see how sometimes with Euler you can jump down. And same for FID. So that's quite good. But not only that, if you've trained again with Adam, sometimes what you know happens is that you get very good performance relatively quickly, but then performance degrades. So you often have to make sure that you save your model often if you want to have the best model, because you might just be for example, not save your model. You will only save it here and here, and then you've lost the best performance part. But what happens with ODE GAN, so using RK4 plus the regularizer, is the performance doesn't drop. You don't have this issue that you kind of get to a point and then you go back again. And it obtains very good performance as well. So this part of the talk was about replacing Euler updates and replacing gradient descent with RK4 in GANs. And we saw something very interesting. We saw that it improves performance and stability. And of course, we saw again this underlying theme of the explicit regularizer. So this is a bit interesting because if we look back at what we've seen so far, we've seen that the drift has beneficial regularization effects in supervised learning, but in GANs, you get a beneficial effect by reducing the drift. So how can we square these two results out? And this is where the work that I've been part of kind of came in, trying to answer this question: why do we see these different behaviors in between supervised learning and GANs? And the way we try to answer this question is, let's try to quantify this discretization drift of gradient descent in two-player games. So going back to that approach of using backward error analysis, but in the context of games. So again, I'm going to introduce the notation. We have our ODEs that directly derive the system. We can write this in a very general way. Of course, if f and g are negative gradients, we end up with gradient descent. And we're going to use numerical integration. Now I'm going to go a little bit into a bit of detail here because it will be important later for the experiments and some of the losses. You have two players, So now you can choose, you have a little bit of leeway of how you can train these players. So for example, we can choose when we use numerical integration from the ODE on the left-hand side to use different learning rates for the two players. So this is one, we're going to assume that the first player has learning rate alpha times h, and the second player has learning rate lambda times h. Now there's something else. If you've trained GANs, you know that we often don't update both players at the same time, which is what's called simultaneous Euler updates. And this is what, or simultaneous gradient descent, and this is what I'm showing on the slide. But what you might have is that you say, oh, I'm going to update the first player, let's say the discriminator often in GANs, and I'm going to take the updated value and use that to update the second player. And this is what's called alternating Euler updates. And what we will want to do is to understand both of them. So that means we have to do backward error analysis twice, because remember, in backward error analysis, we always start with the discrete dynamics, they're fixed, and we obtain a modified ODE. And yeah, just to make it very clear, if f and g are negative gradients, we obtain simultaneous or alternating gradient descent. And just to remind you of the approach, we're going to use a modified ODE to better describe the dynamics of gradient descent. Of course, things are a little bit more complicated because we now have two players. And we need to account for the interaction between the two players, because remember, the update function for the first player depends on the first and second player parameters, and it's the same for the second player. So things get a little bit more complicated. But backward error analysis tells us the form of the modified ODEs that we're looking for. So they're very similar, is exactly the same with what we've seen so far, only that we have two functions to find out. We want to find a function that allows us to quantify the drift here for the first player. This is what we're going to call F1, and the same for the second player. These are going to be F1 and G1. And our goal is to find these. Again, it's going to be by construction. And of course, if you follow the path that I've shown for supervised learning, you will obtain, again, by construction, F1 and G1. I'm not going to go through the proof here. The proof is in the paper if you're interested to have a look. But I do want to highlight something. So here I'm just showing the results. These are the modified ODEs for simultaneous Euler updates. And something that's extremely important in the context of games is that F1 and G1 have each two terms. So now you have, to quantify the drift of the first player, you have a term that only depends on the first player's update function. But you also have a term that depends on the other player's update function. And this is what we call the interaction term. So to quantify the drift of the first player, you also have to know what the second player is doing, just because the two players are so interconnected in terms of change in parameters in continuous time. And it's the same for the second player. Now, if we do the same exercise for alternating updates, the modified ODEs change. So what happens is that for the second player, the interaction term that depends on also what the first player does is now multiplied by this term, which depends on alpha h over lambda h, so alpha over lambda, which is the learning rate ratio. So we will see that the learning rate ratio between the two players is important. And I just want to pause a little bit. One thing that is already very nice is that we have different ODEs to describe alternating and simultaneous gradient descent, which is something that we didn't really have before. And actually, a lot of the theory in GANs does not tackle alternating gradient descent, because a lot of the theoretical approaches, but not all, use continuous systems, but they didn't really have a way to differentiate between simultaneous and alternating updates. Just to build a little bit of intuition, so now we have these ODEs, which we hope better describe the discrete updates. And we can plot this in a small example, just like we've seen in ODE GAN, where we have here original flow. So this is the continuous system, follows the blue trajectory. The Euler updates, so the discretization follows the orange trajectory. We see that these trajectories are quite different, and this is exactly the drift. So the distance between these is the drift. But using the modified ODE that I've just shown before, we have an ODE that much better captures what gradient descent is doing. And we can do the same for alternating Euler updates. We use the other modified ODE that we found. And we see that even though Euler updates follow a different trajectory than simultaneous, alternating updates follow a different trajectory than simultaneous updates, our modified flow is also different, so it's able to capture that. And of course, we also have the case of the divergence. Remember, this was the intuition that I gave with ODE GAN, that sometimes they wanted to use a higher order integrator to avoid this issue with the divergence here. And even in the divergence case, the modified flow is still following what gradient descent does. And the question here is, well, can we use this modified flow then to say, oh, there will be divergence, or there's not going to be convergence around the equilibrium? And there's a tool in continuous analysis that allows us to do this, and that's stability analysis, which basically says that we should look at the eigenvalues of the Jacobian of the gain. And using the modified ODEs, we can write a Jacobian of the modified gain and really answer these questions as well. And what we see theoretically is that we can predict, let's say for this case exactly, using this stability analysis, we can predict what happens in practice, which is that simultaneous Euler updates here diverge, but alternating Euler updates converge. So we don't have to necessarily implement this, but use a theoretical tool to predict what will happen. But this has been so far quite general. We have talked about this kind of form of modified ODEs for very general class of games. So now I'm going to zoom in a little bit to some special types of games that you probably know, and again, including GANs, which I'm going to talk about in a second. But first, let's talk about common payoff games, which are very simple in some sense, but I think they can give us a little bit of intuition of what the drift is doing, as well as the difference between simultaneous and alternating updates. So in common payoff games, both players have the same loss function. So just like in supervised learning, you're minimizing one function. And the way to think about this is that you can think of the two players as partitions of your neural network parameters. So if I have 4 layers, I can choose, the first 2 layers are the first player, the second layers are the second player. And what's nice is that now we can do the same exercise that we've seen in supervised learning to go from modified ODEs to modified loss functions. I'm not going to go through the math here, but just write f and g as the corresponding gradients, and then we end up with this modified loss for simultaneous updates. Now, what's important here is that we do recover implicit gradient regularization, so the supervised learning case, for equal learning rates. Because what these regularizers say is, well, this one says minimize the gradient norm of the first part of the network, and this one says minimize the gradient norm of the second part of the network, but they form a partition. So you can equally write this as minimize the gradient norm for the entire parameters in the network. And this is the same for the other plane. And this is exactly what implicit gradient regularization does. So now we can be breathe relaxed. There is some consistency here. If our game is a common payoff game, so basically as in the context of supervised learning, and we have equal learning rates, we recover the supervised learning case completely. But we can do something else. We can say, well, I want to update my first part of the network first, and then my second part, or the other way around. So now we have a bit of leeway on how we want to update the network. Even though the players have the same loss, we can choose to do alternating updates. We can go through the same exercise and write a modified loss. Now, this modified loss for the first player is the same. For the second player, remember, I drew the attention to this term that depends on the learning rate ratio. Now, this term is very important because it can change the sign of this regularizer, of this implicit regularizer. If alpha over lambda is 1, this is going to be -1. So for example, for equal learning rates, but when I'm updating my first part of the network first and then my second part, what this term says is maximize, don't minimize, maximize the gradient norm of the first player. Now, based on what we've seen in implicit gradient regularization, we should suspect that this is not a good thing, because we saw that minimizing the gradient norm has this positive regularization effect. And indeed, we verified this empirically, that alternating updates in classification, this is an MNIST result, it's more unstable compared to simultaneous updates, and performs slightly worse, but also the gradient norm that this second player is maximizing now is higher in alternating updates than simultaneous updates. So now we are able to, again, take this theory from something quite theoretical on modified ODEs to modified loss functions, and then look at what happens in practice and verify that prediction empirically. Now we can switch to the completely other opposite spectrum of games, which is zero-sum games. So in zero-sum games, whatever one player is maximizing, the other player is minimizing. And again, we can do the exercise of going from writing F1 and G1 as negative gradients, then writing the right-hand side of both ODEs as negative gradients, and go from modified ODEs to modified loss functions, which better describe the dynamics of gradient descent. So we first write out the simultaneous gradient descent case. And the modified loss functions look like this. So we have, of course, the original loss functions. And remember the self and interaction terms. Now, the self term says the following: minimize your own gradient norm. This is very familiar. This is what we've seen before in supervised learning as well. Now, the interaction terms are a little bit more pesky because they say maximize the gradient norm of the other player. But we've just seen in supervised learning that this maximization can be problematic. So one idea that we had is, how about we use explicit regularization to just cancel this? We just add to our loss, to our original loss E, specifically for each player to cancel this, this term. So it's exactly the same term, but with a plus instead of a minus. And what we see is that this really improves performance compared to SGD. So if we have, again, with a zero-sum loss and simultaneous updates, if we cancel the interaction terms, it looks like this. SGD looks a little bit like this. So more stability and higher performance. What we also see is that we can obtain the same peak performance as Atom. So Atom can get to a higher performance quicker, but again, degrades. But the canceling the interaction terms just with vanilla SGD. So here in the blue line has no momentum, no second order information. It's just, we're just going to move the, we're just going to use explicit regularization. We obtain quite similar performance. So that's on the simultaneous updates case. How about alternating case? Because especially in the GAN context, we're really interested in that because this is what people use in practice. And again, the interaction term of the second player changes because it depends on this term that depends on the learning rate ratio. And again, this term can have positive sign or minus or negative sign, and that can change the sign of this term. But as we've just seen, now we kind of want it to flip the sign, because then if we do a plus here, we are again minimizing the gradient norm of the first player, not maximizing it. And indeed, using this approach, we can actually predict which learning rate ratios perform best. The ones for which this is negative and this term becomes a minimization term will perform better in practice for alternating updates in GANs trained with zero-sum losses. So again, we've gone from this very theoretical prediction to a more practical insight. Now, if you're familiar with GANs, these explicit regularization methods, which add the gradient norm minimization, might be somewhat familiar. There are 2 points that I want to make here. So the first one is that the drift is not explicit, it's implicit. If you use gradient descent to train GANs, there's going to be those terms there. Now, inspired by those terms, we can construct explicit regularization methods like the ones that I've just shown. And these can be similar to SGA, if you're familiar with that, or consensus optimization, with the difference that our coefficients are non-hyperparameters. The coefficients are given by the learning rates. Our math tells us which coefficients to use. And also we see empirically that if we compare canceling the interaction terms with SGA or consensus optimization, we do perform better here. And that these other methods are quite sensitive to the coefficients used. But again, we don't have to choose a coefficient. The coefficient is given by the learning rate. Something that I didn't cover here is that often when you train GANs, for example, you train the discriminator 3 steps and then 2 steps for the generator. And the math is there in the paper. I just didn't have time to go into that as well, but we do cover that. So to summarize this part, we started by being intrigued by, oh, why does reducing the drift help GANs? And we went through the higher goal of saying, how about quantifying discretization drift in games? And then we see the importance of the self term and the interaction term, and how the interaction term can really destabilize the game. So these are the 3 papers, or the 3 main approaches that we talked about today. Implicit gradient regularization in supervised learning. If you are training a supervised learning model, this is a very useful effect to know about. Minimizing the gradient norm is something that automatically gradient descent does, but adding further explicit regularization can help. ODE GAN has shown that higher order integrators can really help GAN. So if you have if you're training GANs, you might want to consider not training GANs using gradient descent, but using RK4, because that can be more stable and you don't have to, let's say, monitor necessarily like your training that much. And in the discretization drift into player games work, we try to understand the discrepancy between these two. And we see that, oh yeah, the drift in zero-sum games or in adversarial games like GANs can be destabilizing. So maybe this is why we see this behavior. We were motivated by the first 2 works, and we ended up with that. And one thing that this is just to say that I didn't talk about is stochasticity. And if you're interested in this line of work, there's a really great paper called On the Origin of Implicit Regularization in Stochastic Gradient Descent by Sam Smith and his collaborators that takes very similar approaches. So if you've seen this talk, it should be easy for you to look at the paper, because again, they construct modified losses that accounts for stochasticity as well. And that's it for me. If you have any questions, or let me know, and I'm happy to answer them now or via email later. That's it. Thank you.
Thank you very much. Brilliant. And yeah, I see there is already a question from Mark. Not sure. Mark, do you want to ask your question, or you want me to read that?
I'm happy to ask my question. So yeah, first off, thanks very much for a super interesting talk. What was great was that it was really helpful to have like the tour all the way from the start all the way up to your work on GANs. So that was really helpful. I guess my first question was about the motivation in the supervised learning. So it seems like the additional regularization becomes more important in the GAN setting, but I first just want to understand more how it works in the supervised setting. So I just want to understand more about the reasoning behind this modified ODE. So essentially, we know that if you take the step length to 0, then SGD converges to the optimum, a local optimum of the objective function that you define. So what's interesting about your kind of modified objective function is at least that if you take the step length to 0, then your modified objective function is the same as the original objective function. Did I understand that correctly?
That's exactly right. And that should be like that exactly because of what you said, because the drift is only there in proportional to the size of the learning rate. If your learning rate is really small, then yeah, the drift will not matter, and you want your modified losses to reflect that. Absolutely. Yeah. And yeah, the reason the modified ODE and the modified loss is important is because our step sizes aren't close to 0. Yeah. But that's exactly right.
So I just had a follow-on question from that, and if I'm taking up too much time, please tell me to, and I can ask it later maybe. But so if you have, let's say that your objective function is just a quadratic in the parameters, then there is a step length that doesn't have to decay to 0, that will still allow you to converge to the minimum. Now, what's interesting is that your modified objective function would still be different in that case, if I understand it correctly.
Yeah, I think that's a very good point. So yes, it will be different for non-zero learning rates, but what is important is that in supervised learning, you will still get to that local minima. That's the difference between games and supervised learning. The modified loss, if you have a stable equilibrium in supervised learning, the drift doesn't change the nature of that equilibrium. But in games, remember how I showed this really nice plot where you go to zero, but the gradient descent does not? That doesn't happen in supervised learning. And they actually, if you're interested in that, they have a proof of that in the paper. So in their appendix, they specifically answer this question.
Yeah. Okay. So I'll definitely look into that because, but I won't. I don't think I'll be able to understand that in the next 2 minutes. But am I correct in understanding, at least in the supervised case, that even in cases where gradient descent would converge to the minimum of the original objective function, your modified objective function would actually have a different minimum?
No, so because when you're at a local minimum on the original function, your gradient is 0, and because your because a local minima has a gradient in 0, and the implicit gradient regularization term has a term that depends on the norm square. It doesn't change. Like if
so your objective function is it has the same minima, but it has a different shape elsewhere. Right. Okay, that's super helpful. So in that case, what you can say is that that's really a very cool property, is that you don't change the location of the minima where you might converge to in infinite time, but you definitely do kind of understand how your training dynamics change. Right.
I mean, it's also to say that I think when you use this in practice with deep learning, it's unclear exactly where you. So
I completely agree. Yeah.
Right. It's a lot more complicated in the deep learning setting. But if we talk, for example, of the simple example that you showed, a quadratic, then yeah, absolutely, you're still going to get there.
But also in the case of finite time optimization, you will end up at a different point with the modified objective function as well.
Yeah.
All right, that was very helpful. Thank you very much.
Yeah, no problem.
Thanks, Mark. Any other question? You can raise your hand or just type that in the chat box. In the meantime, I have a couple of questions. So if people are not raising the hand, in the meantime, I can ask mine. So I had like one really extremely theoretical question. I'm not sure now if it's appropriate in this during the meeting, but I was wondering. So when you do this, you are like introducing a regularization. So the reason why you go faster, or sometimes you go to the minimum, is because you are reduce the error as you were showing, and this impact on the conditioning of the problem. So I was wondering if you have done any study about how the condition number of the problem may change, so how the error propagates before and after this regularization.
No, I'm not aware of having looked at that. So I think what we see, especially in the context of GANs, is that you can converge when you didn't converge, and this was what we were focusing on right now. But I think that's a good point. We didn't look at that yet.
So the reason why, okay, great. And yeah, but then I have the like more high-level question. I was wondering, so you were showing a few examples, super interesting, but I was wondering if you have applied this kind of approach to big systems.
Right. So the GAN work that I showed is, I mean, I think that the networks are pretty big. They're like tens of millions. of parameters. So
Okay,
they're
okay.
trained on basically generating CFAR10 images. And I think if I
Okay.
remember correctly, I mean, there are at least, I think, 10 million parameters each.
Yeah, because I was wondering how much this will affect the complexity, but probably you have a benefit because it converts early. I don't know, but I was just wondering if you had any tests which was really big, and so I will check the papers.
Yeah, I mean, I think this is a pretty for GANs, this is a pretty useful use case. I mean, the only one that is bigger would be ImageNet, which I think is like a different level of complexity, but we haven't tried that yet.
Okay, great. Super interesting, Mihaela. Thank you very much. Let me just check if there is any final question, comment. I don't see any. Anyway, in case you you have questions in future, you can always reach Mihaela by her email address. I'm not sure you want to type your email address in the chat box. And so thanks everybody again for, yeah, so Mihaela has just shared his email address. So thanks everybody again for joining us today. And thanks again, Mihaela, brilliant talk. And hopefully we can meet in person in the near future. And thanks again. Thank you, everybody.
Thank you. Bye.